Now, in this video, we're going to be looking at setting up triple integrals to calculate the volume. And I've actually deliberately chosen one example that can be done relatively easily in one of the three coordinate systems, and then one example which is just appalling in all of them. Just to go through the steps for the process. Again, sometimes you can go through the steps and you can get your system set up, but then you don't really want to integrate it in the coordinate system you've chosen. And sometimes it's just a matter of identifying the least worst option. And sometimes that's going to differ from person to person. You may feel better about one particular set of integral calculations than another. So again, visualizing the problem is kind of our biggest challenge. And so we're going to start with an example that is a little bit easier to visualize. That is the volume bounded by the graphs of this upside down paraboloid 9 minus x squared minus y squared, and the upright paraboloid x squared plus y squared minus 9. So essentially the region that we're looking at, we have this upside down paraboloid and we have this upright paraboloid, and we're trying to calculate the region in between them. So we're going to start with rectangular coordinates and set this up and see what that does. So the first thing to do, we want to find the point of intersection. What is the widest point of the graph so that we can set up our integrals. So we're going to set these two z equations equal to each other, and we're going to end up with a circle here as our boundary, which is why this is going to be easier in cylindrical rather than rectangular. But we have a circular boundary, and so if we're going to solve for y, then we're going to have a positive square root and the negative square root as our boundaries in the y direction. And then since this is a circle with radius 3, our x coordinates will go from -3 to 3. Now this is our circle in the plane. And if we look at our integral, again, our lower bound is the upward facing paraboloid in z. The upper bound is the downward facing paraboloid in z. That makes total sense. In the plane, our widest point is the circle of radius 3. And so our lower bound is this bottom part of the circle. The upper bound is the top part of the circle. And then we're going from -3 to 3. This is totally reasonable until we want to try to integrate this. And we would probably require trig substitution to do that. So again, it's easy to visualize. It's not completely insane, but we don't really want to do trig substitution if we don't have to. And so rectangular is maybe not the best way to go. So what we can do is we can try cylindrical. Now, if we scroll down to cylindrical, first thing we're going to do is we're going to rewrite our two equations in cylindrical form. So x squared plus y squared is equal to r squared. So we get 9 minus r squared for the downward facing paraboloid, and r squared minus 9 squared for the minus 9 for the upward facing paraboloid. And then again, these are our z boundaries. Great. We set our two equations equal to each other to find r, and we get r equals 3. That makes sense because earlier we had a circle of radius 3. So our limits will go from 0 to 3. And then we need to go all the way around the circle. And so our limits in theta will be 0 to 2 pi. And we end up with r dz dr d theta between our two paraboloids, 0 to 3 and 0 to 2 pi. And this is really the easiest one to do. And it's really clear why this is easier than rectangular coordinates. Our limits of integration for the outer boundaries are just constants. And I only ever have to deal with polynomials. And in terms of integrating, I don't have to deal with trig substitution. Now, one might hope that in the previous example, that if you had to plug those into squared terms, that maybe the square roots would go away and you wouldn't need trig substitution, but maybe not. Now, if we try to do this in spherical, this turns out to be really hard for this particular problem. So first we have to convert our coordinates into spherical. So we have to transform all of them. And what we end up with is rho cosine phi is equal to 9 minus rho squared sine squared phi. And rho cosine phi is equal to rho squared sine squared phi minus 9. But then I need to solve for rho. And so if I put all of my rho terms on the other side and I try to isolate my rho, I'm going to actually need to complete the square and do all kinds of terrible algebra in order to isolate rho. And my upper limit for rho is then going to look like this hideous contraption. And my lower limit for rho is going to look very similar. Upper limit, lower. I think this is the upper limit, this is the lower limit because of the minus sign. Now, to be clear, we're going to have to set up for phi, we're going to have to set up an integral from 0 to pi over 2, which will take us to the plane, and then another one that will take us from pi over 2 to pi, because it has a different boundary on top and the bottom. But fortunately, since our graphs are symmetrical, we can just calculate the top half and then double it. And when we set up our integrals, we end up again with this 0 to 2 pi, that's our theta, 0 to pi over 2, that's the top half, and I'm multiplying by 2 for symmetry. And then my limit is this monster, my upper limit for rho. And if I integrate rho here, I'm going to get rho cubed, and then I'm going to have to plug in this crazy contraption and cube it. So we're not going to do that. So again, the whole point here is that you can choose a coordinate system for some problems where it's clearly going to be easier in one coordinate system than it is in another. In this case, spherical is dreadful. Rectangular is bad, but not this bad. And if you actually do cylindrical, it's straightforward and easy. And when you integrate that, you get 81 pi. In fact, all of these answers should give you 81 pi. But can you get to 81 pi with an integral that looks like this? Now, some problems, unlike our first example, they look terrible in all of the coordinate systems. And if you're not careful, you can accidentally produce these. Typically, textbooks, calculus textbooks, will try to avoid problems that are this hideous. But you will encounter problems that are sometimes almost this bad. Now, in this example, we're taking a sphere of radius 3 and we're trying to intersect it with a plane, x plus 2y plus 2z equals 4. And you can see from this graph that, at least fortunately, our plane only intersects with the top half of our circle. That's great. That'll make things a little bit easier. It is certainly possible to get problems where the plane intersects both halves of the circle, and then you will have an even more complicated problem because you'll have to integrate these changing boundary conditions as you go from the top half to the bottom half. Things can get, again, more complicated. But we're going to look at our particular example here where we don't have to deal with that special complication. And we're going to try to set up our integrals. Now, initially, we still have something relatively straightforward for z at least. It's going to be upper half of the circle of the sphere. So it's going to look like this. And then we're going to solve our plane equation for z, and that's going to be the bottom. So this isn't great to integrate, but at least the boundaries are clear. Now, if we want to figure out where these, what the two-dimensional boundary is, we have to set our equations equal to each other. essentially plug this z into the z component, put them into one equation with substitution, and then do a whole bunch of math. You have to square this out by FOILing, and then you get all these extra terms, and then you combine like terms, and you get this equation that has this xy term in it, which just doesn't look great. And finally, if you try to simplify this a little bit, getting rid of these coefficients, you end up with this expression. Now, if you choose to solve this equation or to try to put it into a function-based calculator, like your TI calculator, you're going to need to choose either x or y to solve for, and then treat x like a constant. This is not going to be pretty. You're going to have to do things like complete the square with your y squared and your y terms, where one of the coefficients is an x. It can be done. If you graph this, also, you could graph this implicitly in a program like Desmos these days, although that wasn't available when I was doing this. But if you collect your y terms on one side of the equation, your y squared is here, your coefficient of y, if you factor the y out, is this expression. And then to get your completed square, you would take this expression, divide it by 2, and then square it, and then add that to both sides of the equation. And then that will get you your perfect square on this side of the equation. And then you'll have this crazy expression over here, which you'll have to simplify, and then take the square root of this nonsense, and then move your extra terms with x and 4 over 5 over to the other side of the equation. And you get this crazy expression. And it turns out that your crazy expression is an ellipse, and a rotated ellipse, not on the origin, kind of off the origin, and also at an angle. That's what that xy component does. This is an ellipse. Okay, so this looks atrocious, but I can graph it, and I can have my upper bound and my lower bound to put into my integral. I can also see that if I solve for that radical, I can get the limits on what x has to be. And so when I do that, I end up with this crazy integral. Again, this is my upper bound. This is my lower bound. These are my limits in x. Now, cylindrical, again, we're going to take our x squared and y squared, convert that into r squared, make our substitutions, upper bound, lower bound. Okay, no problem. And then we're going to, I think I have a typo in that integral. That should be a 2 right there, not a 1. And then before we substitute, we're going to substitute this expression for z into our other equation. And again, we're going to do math that's going to make our head hurt. And I'm not even actually going to go through all of it in detail because there is a lot going on here. But if we solve for, we're going to have to basically do what we did with the other problem. We're going to have to get our r's on one side of the equation, collect our r squareds. We're going to get a coefficient that depends on theta. And then we're going to have to complete the square in order to isolate r, because r is our function variable. And when you actually manage to get r isolated, you get, shockingly, an ellipse that's been rotated and shifted off the origin, similar to what we had on the other graph. So they should be the same. And then the limits in theta, because we're going to go all the way around the ellipse, are 0 to 2 pi. And so we end up with this insane expression. I think my limits of integration here, this is the bottom circle, not the top circle, but top half of the sphere. But I think we could flip those. But this R radius is going to be a pain to integrate. Because I mean, the R itself will be bad enough, but then we're going to integrate R and then we're going to plug this in and we may have to square it or cube it or do something else. And spherical is not any better. We get a sphere of radius 3, that's great, but our line is going to look like this. And then we need to solve the second equation here in terms of rho. So if we do that, we get this expression for rho. And then that's going to give us our rho integrals. Okay, so that seems fine to start with. But then we need to do phi. And the algebra that we need to do that for phi is we're going to need to replace cosine theta plus sine theta with some kind of constant. For the moment, we're just going to pretend. And then we need to solve this. And in order to do that, we're going to set up our triangle for some other dummy angle in order to solve for phi. And we end up with phi is equal to the inverse cosine of 1 over the square root of 4 plus alpha squared. And then we have to put alpha back in terms of theta. And we end up with this. And then we start at the z-axis where phi is 0, and then this becomes our upper limit. So you can't add these together because you can't add inverse cosines the same way you can't add cosine alpha plus cosine beta is not cosine of the two angles. So we're kind of stuck with this. And then in theta, at least we only go from 0 to 2 pi. And so we end up with this very unattractive integral. And again, the issue here is that in this particular example, the reason that you don't encounter these very often is because if you're not very careful about how you choose the coordinate systems, are you not very careful about how you choose your planes of intersection, these just random functions intersecting with each other, the algebra is going to completely blow up in your face. And so textbook problems are usually chosen very, very carefully to make sure that the algebra is going to work out. And you're really only going to encounter problems that are this level of nasty, like in bonus problems or things like that. And this is why we created technology. This is why we have numerical integrators and things like that, because we just, there are some problems that they are literally just too hard to do. Even if you can set up the integral, there's no way that you will necessarily want to do this integration. Substituting this expression into rho cubed after you integrate for rho, I mean, the 3 is fine, but substituting this and then cubing it, yeah. So triple integrals, the most difficult thing about them is visualizing them and then figuring out which coordinate system is going to get you the best solution. Sometimes there's no good answer, but most textbook problems are going to be more similar to our first example, where in fact one of the versions is nice. And you can always set them up in any coordinate system that you want, but one of them will be manageable, and then the others will be more or less complicated depending on the particular aspects of the problem. But again, out in the real world, when you leave multivariable calculus, you're going to encounter lots of problems where even if you can set up the integral, there is no guarantee that you will actually be able to integrate it in any coordinate system.